Okay, I'm going to assume that everybody read through chapter 7 or watched the video. Good assumption, not a good assumption?
Wait, what chapters are on the test?
I don't know. We're not even close. We're still a week away from the test. It's next Friday. So we're not done with material for the test yet. That wasn't the question I asked. The question I asked was, did everybody look at chapter 7? Okay. Well, so here's where chapter 7 that we'll do today and chapter 8 that we will do on Wednesday are more extensions of the 1- and 2-step mechanisms that we talked about earlier in the semester, including writing out the multiple steps, talking about stabilities of carbocations. So that's what today is, and what Wednesday will be as well. Because I think the book, whoever wrote the book, they assumed that back in chapter 3 when we talked about the mechanistic characteristics, that using these examples would be worthwhile, because then when we got to this in chapter 7, it would be review. But I don't know that their logic actually holds, because it's key on one thing. Two things. You understanding parts of chapter 3 and remembering it. And I think it's the second part that they don't quite. Maybe Canadian students remember everything, but my experience is that's a tough call. So basically, if you remember back, and I'm going to kind of skip around these slides, which are in Canvas, that the kinetics of the one-step mechanism were that the nucleophile concentration to the first power and the alkyl halide to the first power indicated that it was a one-step mechanism, or at least it gave us the idea of that happening. So this is called an SN2 mechanism because overall the reaction is bimolecular. So when you talk about a one-step mechanism, that's nucleophilic substitution that's bimolecular. So that's SN2. When we talk about a two-step mechanism, which we will on Wednesday, that's unimolecular, so that's SN1. So we're going to put the names to these and not just say 1- and 2-step mechanisms. Okay, so that's the first thing that we need to remember from before. Then, if we think about what happened in this reaction, what happened was that a nucleophile comes in and attacks the carbon with the leaving group, and the leaving group leaves. So if I'm writing the mechanism that way, that's how I would write it, is nucleophile minus reacting with the carbon with the halogen on it, and you have to show those two arrows. Now, because this is a one-step mechanism, it will go through, I'm going to go down to the bottom. So when we're talking about taking our nucleophile, reacting it with an alkyl halide, that's going to be the way the arrows go. The nucleophile gives its pair of electrons to the carbon with the halogen attached to it. We're going to expand our leaving groups between today and tomorrow, or between today and Wednesday. So let's not write just a generic mechanism. Let's write this one. So let's take hydroxide and let's react it with butyl bromide. Okay. So right now I'm going to tell you that this is an SN2 reaction. But after Wednesday, I won't have to, because you'll be able to recognize what kind of substitution reaction it is. Now, there's going to be some hints along the way. For instance, this is what kind of halide is this? Yeah, I know that. I'm looking specifically for primary, secondary, or tertiary. No. Do you have an answer before I spin the wheel of death? All right, on 3, primary, secondary, tertiary. 1, 2. I heard mostly primaries. I heard the start of a secondary. I put the CH2 in there. How many carbons is the carbon attached to the bromine attached to? 1. So this is primary. Now, the other mechanism that we're going to have to choose from is SN1, or the two-step mechanism. And does anybody remember the intermediate that you get with the two-step mechanism? It's a carbon with a plus charge, which is a carbocation. Are primary carbocations allowed? No. So, if you're looking at this molecule, primary halides can only undergo SN2. They cannot undergo SN1 because they can't form a carbocation. So that's some of the hints that we're going to get from the reaction in order to be able to figure out what the mechanism is. And we'll get more of those. So on Wednesday we can make a chart and say, here's how we tell the difference between SN1 and SN2. All right, so my hydroxide comes in, adds a pair of electrons to CH2, and then kicks off the bromine. And in SN2, that leads to a trigonal bipyramidal geometry for the transition state. So I'm going to have a partial bond to carbon, another partial bond, and then I'm going to have a bold and a dashed wedge, and one in the plane. So the hydroxide is going to be partially bonded, the bromine is going to be partially bonded, and then we've got two things. Oops. Then all the other groups that are attached to the carbon. So in this case, it's 2 H's and a propyl group. So that's the trigonal bipyramidal geometry. And that's the transition state. So in the product, if I jump ahead and write the product plus Br minus, the transition state again is the average of the products and the reactants.
Does it matter like what bonds you put the different groups?
Not for the moment, but it will. Maybe. Depending on the problem, it might. But we'll come to that in a minute. So OH goes from -1 to neutral. So its average is delta minus. Br goes from neutral to -1. Its average is delta minus as well. So in the transition state for this reaction, the negative charge on OH is being transferred to the bromine. And then when the bromine leaves, we end up with the alcohol plus Br minus. So SN2 reactions, unless there's a special kind, which we won't get to today, has one step, one transition state. And you have to include these arrows and you also have to include the transition state in the mechanism. And I'll give you at some point in the next few days a take-home quiz where you have to write the mechanisms of SN1 and SN2, and you'll have to do that on the next exam if you're worried about the next exam. So there's something you will have to do. Bobby?
What is the difference between those two arrows you have written down? One looks like you have it shaded in more, and the other one is just
Because
there.
I just drew it. They're both
the same.
they're both full arrows.
No, not in the.
Oh, this. So my problem is when go away. So my problem is that when I have to show a dashed wedge with a dotted line, they look the same. So all I did was make this a dashed wedge. I normally don't do that, but in this case I have to distinguish it from the dotted line of the transition state. So we got a bold and dashed wedge. And if we go back now and we look at in the slides, if we look at that transition state is going to be trigonal bipyramidal, so it's going to look like this. You've got your nucleophile, you've got your halogen in the same line, and then you're going to have the other three bonds being the trigonal bipyramidal geometry. Now, that is not a carbon bonded to 5 things. That is a carbon bonded to 3 things and partially bonded to 2, so that I'm not violating the 5 bonds to carbon. I've only got 4 full bonds. Okay, so in the transition state, that's what we would write. All right, is everybody kind of with me on that?
What does the air, like equal sign and the line through it?
That means, this means transition state. The double dagger is an indication that you have a transition state. Sometimes people will put intermediates in brackets as well. So this just means it's a transition state.
Wait, how'd you determine that it's trigonal bipyramidal?
Because I know it is.
How do we know?
How do we know it is? Because that's the only geometry that can exist if the nucleophile comes in and attacks the carbon from behind and kicks off the leaving group, which I'm going to get into more details about in a minute. Okay. So in terms of the reaction coordinate diagram then, you have one transition state, but what's more important is for an SN2 reaction, you have no carbocation intermediates. When you have carbocation intermediates, that's an indication that you have an SN1 reaction. Okay. And in this case, we couldn't have any carbocation intermediates because we've got a primary halide. So the way the mechanism works is the nucleophile comes in and it attacks the carbon down the same trajectory as the carbon halogen or carbon leaving group bond. So that nucleophile is coming in at that exact line, in that exact pathway. So this is sometimes called backside displacement or backside attack, bless you. And there is the possibility, at least on paper, that the nucleophile could attack from the front. We have evidence that that doesn't happen, but we now know why the nucleophile has to attack from the back. And that is because what's going to happen is the nucleophile has its electron density in the orbital that it's going to use to bond with the carbon. Now, when we talked about sp3 hybridized carbons, there's actually 2 lobes to the sp3 hybrid orbitals. There's the big one, and then there's this little tiny one that we don't normally talk about. But in this case, what happens in order to get this mechanism to occur in one step is that this orbital overlaps with that one. And then the bonds that are already on carbon, what they do is they're pointed this way to begin with. They begin to move until they're perfectly straight up and down. That's the trigonal bipyramidal geometry. And then when the leaving group leaves, they basically, it's like an inside-out umbrella as they move to being oriented towards the right. So here they start out on the left, and here they end up on the right. So as the nucleophile comes in the middle is the trigonal bipyramidal, and then as the leaving group leaves, it switches to the other side. Okay. So that's how the geometry works, and that's how the orbitals overlap. So there's a couple of occasions when we invoke the little tiny sp3 orbital that we normally don't. This is one of them. Okay. Now, the other evidence that we have that there's not front side attack and that it's backside attack is if we decide that we're going to react this with a chiral alkyl halide. So when people first proposed the backside attack, they had to prove that that actually happened. And the easiest way to do that is, for instance, to use R2-bromobutane. And if you use the R2-bromobutane and you have that one pure chiral form, the reactant's going to rotate plane polarized light. Now, I don't know if it rotates it to the left or the right. I'd have to look up and see what the R is correlated with. But it does rotate plane polarized light. So the first question was, if I do an SN2 reaction on this molecule, do I get a product that rotates plane polarized light? Because if I don't, then that means I form the products in a 50-50 ratio, a racemic mixture. But if I do get an optically active product, then that means that the reaction either went by backside attack or frontside attack, and not both. So this is not a trivial experiment to do, because remember, there's no direct relationship between R and S and D and L. So this R compound could be positive or negative, could be D or L. This S compound on the other side could be D or L as well. So what you have to do is you have to look up what the literature value is for the R2-bromobutane and what the literature value for S2-butanol is. And what you would find then is that whatever this rotation is, when they did the SN2 reaction, they got the rotation of the S configuration. So they were able to show that the R configuration became 100% S. Okay. And so what that means is that you have to have backside attack, and that this chiral center is what it undergoes what's called inversion of configuration. So again, the sign of the product does not change. Whether it's D or L or R or S, you'd have to figure out. But what happens 100% of the time, well, what happens 99% of the time and 100% of the time in this class is that the R configuration gets inverted to S or vice versa in an SN2 reaction. And that confirms the fact that we have backside attack. So if I looked at this molecule over here and I put in my numbers, for hydrogen would be 4, bromine would be 1, ethyl would be 2, methyl would be 3. So that means I have a R configuration. If I looked over here, 4H, 1 OH, and then ethyl. If I drew that one, it's S. So that chiral center is inverted. And that establishes the fact that it's backside attack. And then people said, well, why is it backside attack? Then they went and looked at the orbitals for the sp3, saw that little tiny orbital and said, well, that's where the nucleophile needs to attack in order to form its bond, overlap its orbitals to form its new bond. So we now know it's backside attack. Now, the reason I said it's only 99% probable that the chiral centers invert is because this is hinged on one critical thing, that the group that's being replaced is replaced by another group that is ranked number 1 in the Kahn-Ingold pre-Lux sequence rules. So you have to be replacing a number 1 group with another number 1 group. And in this class, that will be the same, although now that I've said it, I could think up some examples where maybe it wouldn't, but I'm not going to do that. I don't have the ambition and time and energy right now. But in other molecules, you may actually have the chiral center will be inverted, but if it's not the number 1 group after the inversion, you would actually see the configuration stay the same. So when we're talking about inversion, we're talking about the groups going from being oriented this way to basically being oriented on the other side. Okay. And the way that works is, I don't know, this is probably not a good example, but it's sort of like an umbrella. When the wind gust hits it, it inverts. It goes inside out. You'd have to figure out how to orient that with these two molecules, but that's essentially what you're looking at when you're looking at the umbrella pointed this way and then the umbrella pointed that way. That's the classical example that's used. So what we know about SN2 is it's bimolecular, it's one step, one transition state, and that now, since we know about chirality, that if you react to chiral center, a molecule with a chiral center, you're going to make an optically active product, and the chiral center will undergo inversion. So we've added on to what we talked about back in chapter 3. A lot. But the mechanism still remains, writing the mechanism still remains the same. You still just basically have 2 arrows, one for the nucleophile coming in, one for the leaving group being kicked out, the trigonal bipyramidal geometry, and the final product. And that's what the last slide in this set will show you. It'll give you those details. Now I do want to go back and talk a little bit about reactivity. So if you look at reactivity, you're going to find that since it's an attack on the nucleophile on the halide or on the carbon with any leaving group, that it's going to be based on sterics. So the least sterically hindered, the more likely the reaction or the faster the reaction is going to occur. So primary alkyl halides will react the fastest, and what I did was I added a sort of a addendum here that says methyl halides react the fastest of all. Because if you have a methyl group, then you don't have any alkyl groups to provide hindrance. And so my example here is that a molecule like methyl iodide is actually I don't know, it's a teratogen, which means that it could be it's definitely a teratogen. It could be considered a mutagen, because if you get methyl iodide in your system, if you're working with it, you breathe it in, or somehow it gets through your skin, what happens is that methyl iodide will react with a lot of different nucleophiles in your body. And it'll start adding methyl groups to things. That process is called methylation. So the last thing you want to do is start methylating or mutating DNA, RNA, enzymes. In the movies, that gives you like superpowers. Probably in real life, it gives you death. So, or it gives you something in between. So when you have a methyl halide, those are all really considered to be sort of mutagens and bad. They're not good. You have to be careful when you work with them, particularly the iodide, which we'll get to why the iodide in particular. Now, molecules that do not undergo SN2 are tertiary halides, because there's too much steric bulk here amongst the three alkyl groups for the nucleophile to get to the carbon. And what we say with the complementary reaction SN1, which is the one with the carbocation, is that primaries don't undergo SN1 because you can't have a primary carbocation. But what about tertiaries? What was the most stable carbocation? A tertiary one. So whether we're dealing with chapter 7 with SN2 right now or Wednesday, we have to take the two of them together. Because tertiary halides will undergo substitution, but not by an SN2 mechanism, by an SN1 mechanism. Halides that are attached to a double bond will also not undergo substitution, because basically the carbon has to be sp3 hybridized, and that carbon is sp2. So sp2 hybridized carbon with halogens attached, they do not undergo substitution. And my benzene ring over here, the circle means that we have alternating single and double bonds. The nucleophile trying to do backside attack on that carbon with the halide is going to be blocked by the entire ring, let alone the fact that it's attached to a double bond. So those molecules do not undergo SN2. So that's the basics of SN2 and the one-step mechanism. Although we will have some two-step mechanisms, but they will not involve carbocations, or they will not involve carbocations, which makes them a two mechanism. Now, as far as the steric hindrance goes, I used to have this as a sort of standalone PC program that would run, and this thing would like come up here, and then you'd see the product on the other side. That software is long since out of date and doesn't work anymore. And these slides are all I have left of it. I don't even have the original ones. So when the nucleophile is coming down to attack the carbon with the halogen, remember that this carbon is delta plus. That's why it's attacking that carbon. You can kind of see that for a primary halide, there's enough space there for it to overlap orbitals. For a secondary halide, less space, but still doable. All the secondaries are going to be the ones that we'd have the most problems with, because as we're going to remember on Wednesday, secondary halides can also form carbocations. So secondaries can do both SN1 and SN2. And so they're the ones that if we spend too much time on, we're going to get totally confused. So we're going to kind of leave them by themselves for the moment. And if I take this secondary and let's say I put a terse butyl group on this position, Now I can actually make it so sterically hindered that that molecule would not undergo SN2, because there's no way for the nucleophile to get at the carbon that's delta positive. And then a tertiary, too much steric hindrance. So the basis for SN2 is steric hindrance of the alkyl halide. Or it could be the steric hindrance of the nucleophile, but give me a couple days and we'll talk about that later. Josh?
The little mini sp3 orbital is still there regardless of all the steric hindrance.
Yeah, it's still there, but this nucleophile with its orbital, it can't really get there because of the way that these three groups are blocking it out.
So it has to be SP3, but then based on the steric hindrance, that can prevent it. So that's how you know which one's worse.
Right, so that's why primaries are faster than secondaries, and tertiaries don't undergo SN2. It's totally, SN2 is based on sterics. And again, if you remember back, SN1, the multiple step mechanism, is based on the stability of the carbocation. So after we talk about that on Wednesday, we're going to put everything together from an SN1, SN2 standpoint. And then there's E1 and E2 for eliminations, and we'll get to those on Wednesday and next week, or Friday and next week. But the critical thing to remember is a 2 mechanism does not have a carbocation intermediate, but a 1 does. And that's what I'm going to harp on for the next week. All right, so is everybody kind of with me? And will you be with me after you go and watch the video or go through the book? Yes. Will you be that way at the beginning of class on Wednesday? If you can possibly be that way. Okay. Now I understand if you go through and you're like, I need to see it first and then go back. That's fine. But then if something doesn't make sense, if I blow through something that you don't quite understand, you got to say, wait, can you go back? Or you start at the beginning when I say, are there any questions? Then you can say, I didn't quite understand this part, or I didn't understand the whole thing, which is not helpful. That's like the student who plopped the book down in front of me and said, I don't understand. I said, what don't you understand? He goes, chapter 3. And I said, what in chapter 3? He goes, the whole chapter. And I said, get away, go. Come back when you have a question. Not understanding the entire chapter is not a question. So that can happen. All right. So what I want to talk a little bit about is I want to talk about leaving group ability. So right now we have leaving groups that are only halogens. But what makes a good leaving group? And then I want to talk about what makes a good nucleophile. Can we rank the strengths of nucleophiles from strong to weak? So with leaving group ability, it's pretty straightforward. There's one thing that affects leaving group ability, and that is basicity. And it's an inverse relationship, meaning that the stronger the base, the weaker the leaving group, and vice versa. So if I want a good leaving group, I want a weak base. So right now we've got halogens. Let me expand this a little bit, jumping a little bit ahead to maybe next semester. But here's something that is an outstanding leaving group. Okay. So this oxygen would be attached to a carbon, and then when it leaves, it's going to have an O-. So this is what's called a tosylate. So what makes that an outstanding leaving group? You tell me. Is your hand up or not?
I don't know.
You don't know if it's up or not?
It has a multitude of ways that it would be able to stabilize its negative form.
Okay, stop there. So I can stabilize this molecule by doing what? What's going to stabilize this molecule? Resonance. So there are multiple resonance structures, and what are those resonance structures ultimately going to do? Disperse the charge to what atoms? Which ones? The oxygen. So by writing resonance structures, I'm going to be able to disperse, I like delocalize, to delocalize the negative charge, spread it out to the other two oxygens. And that's going to ultimately cause this molecule to be more stable. And if this molecule then becomes more stable by the ability to draw resonance structures, the more stable structure means it's going to be a weaker base, so a better leaving group. So we can put all those things together in the fact that this is a very stable structure because it has resonance structures to spread out the negative charge to the oxygens. The more stable it is, the weaker the base it is. The weaker the base it is, the better it is as a nucleophile. Okay. So this is the way we have to think about this. Okay. So leaving group ability is based only on basicity. That's it. Now, what about nucleophilicity? Nucleophilicity is how strong that molecule is as a nucleophile. Okay. And this is going to depend on a couple of things. It's going to depend when we're looking horizontally on the periodic table. It's going to depend on basicity, and it's going to depend directly on basicity, meaning that the stronger the base, the stronger the nucleophile when we're looking horizontally. So that means that a C minus and an H minus, they're comparable. They're stronger nucleophiles than an N minus, stronger than an O minus, stronger than an F minus. Because it's totally based on basicity. Now, the problem is when we go vertically on the periodic table between F and Cl and Br and I, when we go into a vertical relationship, it turns out that the bigger the anion, the better it is as a nucleophile. So in this case, as you go down the periodic table, nucleophilicity increases.
What does that say on the top? Basicity is what?
Direct. It's a direct relationship. It's a direct relationship. So stronger the base, stronger the nucleophile. So the reason that happens is because of what we call polarizability. When you're looking horizontally on the periodic table, polarizability is what rules. When you're looking horizontally, let me start all over again. When you're looking vertically, polarizability is what's important. When you're looking horizontally, basicity is what's important. So basicity is the horizontal relationship, polarizability is the vertical one. Now, what is polarizability? I call polarizability squishiness. And this has to go back to the idea of the nucleophile taking its electron density in its orbital and overlapping it with the small orbital of the carbon in the SN2 reaction and in the transition state. So what happens to atomic size as you go down the periodic table? It increases because you're adding more electrons, right? So the same thing's true for an anion. As we go down the periodic table, the nucleophile gets larger. Now, as it gets larger, that means those outer electrons aren't held as tightly to the nucleus as they are when the atom's smaller. So when you have less firmly held electron density, you can move it around. And that's the squishiness. You can move it around and you can concentrate more of the electron density in the orbital that's then going to overlap with the carbon. Okay? And when you have something like iodide that's huge, you're going to have that ability to take that electron density and compact it. If you have something like fluorine, which is more like a golf ball, as opposed to iodine maybe being like a Nerf ball, if we still have Nerf stuff. I don't know if we have Nerf stuff anymore. See, stuff that I grew up with is gone. Or it's considered vintage now. So when you can squeeze things, it's going to be squishy, but like a golf ball would be fluorine. It would be really hard to move electron density around. So that means as we go down the periodic table, nucleophilicity increases because of polarizability. So that means that iodine, in the series of bromine, chlorine, fluorine, and iodine, iodine would be the best nucleophile. Now, OH minus is better than all the halogens. But iodine's better than fluorine. Now, I guess I didn't do that back here in the leaving group ability slide, so maybe we should do that. Maybe we should go ahead and rank fluorine to iodine. Which one is the best leaving group? And so I'll give you a chance to earn some participation points for today. So tell me which one would be the best leaving group. Fluorine, chlorine, bromine, or iodine? 14-14 tie. Same thing happened this morning. So, what I did this morning was I asked them to talk for a minute. Since I'm already basically at my time limit, let's kind of just quickly go through this. So, I want the strongest. Why did it get small? Okay. I minus, F minus, or I minus. Which one's the stronger base? Well, you're probably going to answer that in a 50-50 split too, right? So how about which one's the stronger acid, HF or HI? HI. HF is a weak acid because it only partially dissociates in water. HI completely dissociates in water. So if this is the stronger, if HI is a stronger acid, which one's a stronger base? Stronger base is F minus, right? So this is a stronger acid, it's going to have the weaker base. So F minus is the stronger base. And so that's going to make I minus the best nucleophile. The best leaving group. But then you also saw that I minus was the best nucleophile. So what that means is, when you're doing halogen-only SN2 reactions, you want to stay away from iodine because iodine's the best nucleophile and it's the best leaving group. So what that's going to do is it's going to give you equilibrium products. Okay? So you notice that we've got a lot of inverse relationships here. So where we're going to start on Wednesday is we're going to start with a quiz where I'm going to ask you about trends in terms of basicity and acidity on the periodic table, as well as then a couple rankings, like which one of these is the best leaving group, which one of these is the best nucleophile, and we'll do that with your device at the beginning of the lecture. Okay? And then we're going to talk about Chapter 8, which is SN1 reaction.
And that's not participation, that counts as like real points.
That counts as a quiz, yes. That is a quiz like a take-home quiz, which you'll have some of those too. Okay, so you need to know what the relationships between basicity on the periodic table is, where the polarizability, leaving group ability, as well as nucleophilicity. All right, so that's how we'll start on Wednesday.